Hi folks, this revision video is about obtaining and using metals. It is the topic that's taught you in year 10, not by your chemistry teacher, but it is a chemistry topic. And quite a lot of it's foundation, but quite a lot of it is also higher. So I will take you through everything. Slides that are higher have an H, and slides that are super higher have an H plus. So an H plus would be 7, 8, 9, and an H would be kind of 6, 7, but it would be a little bit more high 7, 8 and 9 if it's got a plus. Okay, so you guys should already know that some metals are more reactive than others, and you did about reactivity back in year 8. And when we establish reactivity, we heat metals with oxygen, water and acid. And you can see that potassium down to zinc bursts into flames and forms an oxide very vigorously, whereas iron will just glow to form its oxide. Lead and copper form an oxide layer without glowing or bursting into flames, and silver and gold don't react with oxygen in that way, although silver does tarnish, but we'll talk about that later. With water, potassium and sodium produce hydrogen with cold water, but calcium, magnesium, aluminium, zinc and iron need steam to produce hydrogen. Potassium and sodium make hydroxides, and calcium, magnesium, aluminium, zinc and iron make oxides when they react with steam. But lead, copper, silver and gold don't react with steam. Potassium and sodium react violently with acid. Calcium, magnesium, aluminium, zinc, iron. Rate of reacting with acid will decrease, and you'll see less bubbles of hydrogen, and lead is very slow, and then copper, silver and gold don't react with acid. Okay, so that's our starting point. So if we look at that in a little bit more detail, the metals that react with cold water, so your sodium and your potassium make metal hydroxide and hydrogen, and the other metals that have a reaction and they react with steam will make metal oxide and hydrogen. Okay, so that's the ones that aren't quite as reactive as sodium and potassium. Okay, and you can see here the balanced symbol equations as well as the word equations. So the reactivity series comes from how easily the metal atoms lose their outer electrons, and you remember that loss is positive and gain is negative. So when metal atoms lose electrons, they form cations. So just remember, losing electrons is positive, lip, and loss is positive. Okay, so a cation is positive. There's your little cat to show you that cations are positive and anions are negative. So reactivity is very important in displacement reactions, and we know that a more reactive metal, if it's placed into a metal solution, it will react and displace the less reactive metal. So for example, copper sulfate plus magnesium will give you magnesium sulfate plus copper. You will have blue copper sulfate and grey magnesium, and when you put them together, the magnesium is displaced into solution, so the blue colour fades, and then you get orangey brown copper being formed. You should have done this particular practical where you're putting magnesium, zinc, calcium and copper into different magnesium, zinc, calcium and copper salts, and you're looking for colour changes in the solution, colour changes on the surface of the metal, and bubbles of gas being given off. And you should have reacted copper, magnesium, zinc and calcium with copper sulfate, magnesium sulfate, zinc sulfate and calcium nitrate, for instance. And you should be able to look at each one. Can copper, is it reactive enough to take sulfate from magnesium? Clearly not. It's not reactive to take sulfate from anything. Whereas magnesium's really reactive. It can take sulfate from copper, sulfate from zinc, but it can't take sulfate from nitrate. Zinc can only take sulfate from copper. Calcium can take sulfate from any metal you like. And you can see how the number of reactions differs, and the total number of reactions will link to their reactivity. So if you've got 3 reactions, then you're the most reactive, so that'd be calcium sulfate, just calcium. And the second most reactive has got 2 reactions, that'll be magnesium. The third will be zinc, that's got 1, and then copper has none. Okay, so it just helps you to work out the order of reactivity. So Miss Iron and Mr. Sulfate and Miss Zinc comes along, and she can take sulfate away from iron. So iron sulfate plus zinc goes to zinc sulfate plus iron. Okay folks, take a moment to jot down 1, 2, 3, 4, 5, 6 and decide by looking at the reactivity series whether there'll be reactions between these chemicals. So basically folks, iron oxide and magnesium, yes, because magnesium is more reactive than iron. Zinc is more reactive than copper. Potassium is more reactive than copper, but iron has got chloride and it's more reactive than gold. Sodium has got chloride and it's more reactive than calcium. And clearly calcium is more reactive than silver, so it can take nitrate away. Okay, also just very quickly complete these word equations. Pause the video to complete them, remembering your reactivity series. And now you're back, hopefully. Magnesium chloride plus iron. No reaction because potassium has got sulfate and potassium's more reactive. No reaction because calcium's more reactive, it's already got oxide. Zinc nitrate plus copper, copper nitrate plus silver. Okay folks? Okay folks, now things go higher because reduction and oxidation happens at the same time, and reduction can be loss of oxygen and oxidation can be gain of oxygen. But also, if you remember from electrolysis, oxidation is loss of electrons and reduction is gain. So if we look at magnesium plus zinc chloride going to magnesium chloride plus zinc, we can't really see in that simple equation what's happening to the electrons. But if we take away our spectator ions, if we take away our chlorines, which remain unchanged either side of this equation, we can write the equation as an ionic equation. Okay, and that shows us how atoms turn to ions and ions turn to atoms in chemical reactions. Okay, so magnesium atoms plus zinc ions become magnesium ions and zinc atoms. We can see that quite clearly when we take the chlorines away. And remember, you become a positive ion by losing electrons. The chloride ions, as I said earlier, are called spectator ions as they don't change either side of the reaction. Okay? The ionic equation could be split into 2 half equations. The magnesium becomes magnesium ions plus electrons, and the zinc adds electrons to it to become zinc atoms. So if we look at that in a little bit more detail, magnesium atoms are oxidized to become magnesium ions because they've lost electrons. Zinc ions are reduced to zinc atoms because they've gained electrons. And if we put that into our half equations, magnesium loses electrons, and you can see the electrons pulling off it. Zinc ions gain electrons to become zinc atoms. Okay, so we have simple equations, and if we take spectator ions away, the ones that don't change either side, then we're left with an ionic equation, and we can break it down even further to see what's actually happening to the electrons by doing a half equation, and this is higher plus. Okay. So let's take that one step at a time. So here we have a word equation. Magnesium plus copper oxide goes to magnesium oxide plus copper. Simple grade 3 word equation. We can turn it into a symbol equation, and you can see in the symbol equation that the oxygens are part of a compound on both sides of the equation. So the oxide ion is going to be our spectator ion, and we can take it away to reveal the ions beneath. Okay, we ignore our red spectator ions and we take them away, and by taking the red oxygens away, we can see that magnesium atoms become magnesium ions, and the electrons from the magnesium go to copper ions to turn them into copper atoms. Magnesium atoms are oxidized to become magnesium ions, and copper ions are reduced to become copper atoms. Displacement as a redox reaction. We can break that down even further by doing the magnesium atom to the magnesium ion half equation and the copper ion to copper atom half equation. And we can therefore see that magnesium atoms become magnesium ions and electrons, and copper ions add electrons to them to become copper atoms. So we can follow this displacement reaction as a redox reaction. Magnesium plus copper sulfate goes to magnesium sulfate plus copper. Symbol equation with the spectator ions in red because they're the same both sides, they're in compounds on both sides. We take them out. We're left with magnesium plus copper goes to magnesium plus copper ions goes to magnesium ions plus copper. Magnesium is oxidized, copper ions are reduced, and we can use half equations to show that in more detail, to show exactly what's happening to the electrons. Now, we can just take a moment to visualize that in a bit more detail. So here's our word equation, here's our symbol equation. If we take an atom diagram of our symbol equation, we can clearly see the copper ions giving their electrons to the sulfate and the magnesium ions giving their electrons to the sulfate. But if we remove the sulfate altogether, our atom diagram simplifies to show just the atoms turning to ions and the ions turning to atoms. If we look at our ionic equation atom diagram, we can break it down further to show the magnesium atom becoming a magnesium ion by passing its electrons to copper, so that the copper ion can become a copper atom. and the magnesium is oxidized by losing electrons and the copper is reduced by gaining. We could look at our half equations, and there's the model for our half equations. The magnesium atom losing electrons to become a magnesium ion, and then the copper ion gaining those electrons to become a copper atom. Okay folks, if you are aiming for above grade 6, I suggest that you pause and try to write the symbol, ionic and half equations for these word equations. I'm happy for you to look up the formulae for the compounds, but it would be really good if once you've got the formulae for the compounds, if you can write the balanced equations yourself and then the ionic and half equations. If you're going for grade 6 or below, you can leave this page out or this slide out and just move on. Okay, so pause if you're going to do it, but don't worry if you're not. Okay, hopefully you've paused and had a go if you're going for grades above 6. There is your symbol equation, and you can see that I've done the spectator ions in red. They are part of compounds, both sides of the equation, so they can be removed to show zinc atoms becoming ions and lead ions becoming atoms. And then we can write our half equations to show the zinc losing electrons and the lead gaining. Same for iron and copper sulfate. Same for calcium and nitric acid. Same for copper and hydrochloric acid. Okay, if you need any help with these, if you're going for above grade 6 and you need some one-to-one help, then please see me and we'll set aside some time to go through it. Thank you. So we've looked at some trickier stuff. We've looked at displacement reactions. We've looked at them as redox reactions in terms of loss and gain of oxygen and loss and gain of electrons. And now we need to start to think about extracting metals. So metals make up a relatively small proportion of the Earth's crust and are normally found in rocks as ores. So a rock with a high metal content is called an ore. So the Earth's crust is 46% oxygen, 28% aluminium, 28% silicon, but the amount of titanium, potassium, magnesium, sodium, calcium and aluminium is quite substantially smaller, and all other elements are 1%. Okay, so that's not very much in the Earth's crust of metals, but it's enough for us to be able to extract it by uses. So ores, an ore is a rock that contains enough of a compound to extract a metal for profit, and reactive metals occur as compounds in ores, such as oxides, chlorides and carbonates. And here we've got bauxite, which is aluminium oxide, and cinnabar, which is a mercury compound, galena, which would be lead oxide, hematite, which is iron oxide, and malachite, which is copper, a copper compound, probably copper oxide, and that's probably mercury oxide. But very unreactive metals such as gold and platinum are found literally naturally in their native state as uncombined elements just lying about in gold and platinum mines. So unreactive metals can be found as elements and they're called native metals. So gold, silver, platinum can be dug up. All other metals have to be extracted from rocks or seawater. Metals below carbon in the reactivity series, so zinc, iron, copper, silver, gold, and well, not copper, silver, gold so much, because they can be, not silver and gold, but zinc, iron and copper can be extracted from their ores by heating with carbon, as can other metals like lead and tin and that kind of thing. So here is hematite, iron oxide, and iron oxide is heated with carbon to make iron and carbon dioxide. The carbon is oxidized and the iron oxide is reduced to iron. So the carbon is oxidized to carbon dioxide and the iron oxide is reduced to iron. Okay, displacement reactions as redox reactions. So we can use carbon to extract metals from their compounds. Copper oxide plus carbon goes to copper plus carbon dioxide. The carbon is oxidized to carbon dioxide. The copper oxide is reduced to copper. Displacement is a redox reaction. This time we're talking about loss and gain of oxygen as well as loss and gain of electrons. So you've got a word and symbol equation there for extraction of copper from copper oxide. Use that information to help you. You've been given the formulae of the metal oxides, and write word and symbol equations for each one using the patterns from above. So pause the video to do this. And hopefully you're back. This is higher but not higher plus. Lead oxide plus carbon goes to lead plus carbon dioxide. Oh, there is your symbol equation. Zinc oxide plus carbon goes to zinc plus carbon dioxide, and there's your symbol equation. Tin oxide plus carbon goes to tin plus carbon dioxide, and there's your symbol equation. Okay? Right. You can also extract metals using electrolysis. So electrolysis is a much more powerful method for extracting metals. So it can be used if the metal is more reactive than carbon. And an example is the extraction of aluminium from aluminium oxide, which is called bauxite, the metal ore that has a high aluminium oxide content is called bauxite. So aluminium oxide goes to aluminium plus oxygen. And there's the balanced symbol equation. But how are we going to do that with electrolysis? Well, electrolysis of aluminium oxide is complicated. You can see that the whole of the bottom of the tank is the negative electrode, and then there's 3 positive electrodes sticking into our molten aluminium oxide. To save on energy, it has to be dissolved in cryolite rather than just melted. And we have got aluminium, so aluminium oxide it will dissolve, and then aluminium itself has a melting point of 660 degrees Celsius. So it's formed as a liquid after the electrolysis, and molten aluminium comes out. So we've got to work out what's happening at the electrodes. Well, we have got aluminium ions and oxide ions. And the oxide ions, O2-, are attracted to the anodes, the positive electrodes, where they form oxygen gas. That oxygen gas immediately reacts with the carbon of the electrodes to form carbon dioxide. And the electrons that came from the oxygen move through the electrolysis unit to the negative electrode to then collect on the aluminium ions to make aluminium atoms. And we can turn these into half equations. So the aluminium ions are attracted to the cathode where they gain electrons to form aluminium. The oxide ions are attracted to the anode where they lose electrons to form oxygen. Here we have the cathode, aluminium ions gaining electrons to become aluminium, and at the anode, oxide ions breaking up into oxygen and electrons, losing those electrons. The anodes are made of carbon, so the oxygen immediately reacts with the carbon to form carbon dioxide, and the electrodes, the anodes, wear away and have to be replaced. Okay folks, magnesium is extracted by the electrolysis of molten magnesium chloride. The name of the product formed at each electrode you can state, okay, because obviously if it's magnesium chloride you're going to make magnesium and chlorine, you've got to decide which one goes to which electrode, and then write the overall balanced equation. So have a little pause, try those 2 questions, try the challenge, and back in the room. Okay. At the anode, chlorine is made. At the cathode, magnesium is made, okay? And the overall equation, MgCl2 goes to Mg plus Cl2. Okay, so magnesium chloride splits up to magnesium and chlorine. Remember, the anode is positive, so the chloride ions are negative, which are attracted to it, and the cathode is negative, so the magnesium ions that are attracted to it must be positive. And we don't extract all metals by electrolysis because it takes lots of energy to melt the compound, so it's an expensive process. We can also use biological methods to extract copper from ores containing smaller amounts of copper. Phytoextraction involves growing special plants that absorb copper compounds. The harvested plants are burnt to form ash from which copper is then extracted. Bioleaching uses bacteria grown on a low-grade ore. The bacteria produce a solution containing copper ions which copper can be extracted from. The advantage is that they reduce the need to obtain new ore by mining and conserve limited supplies of more valuable ores with higher metal content. But they do take quite a long time. So phytoextraction. Plants absorb copper compounds through their roots. They concentrate these compounds. As a result of this, the plants can be burned to produce ash, and then that ash can be reacted with acid to make a solution from which the copper can be extracted. That's phytoextraction. Bioleaching, bacteria absorb copper compounds. They can then produce leachates, which are acid leachates. This is called bioleaching, and then you can extract the copper from them by electrolysis. The bacteria is mixed with the low-grade ore. Low-grade ore just means it's got a low metal content. Then the acid waste, the leachate solution, has copper extracted by electrolysis. Advantages and disadvantages. Neither of them produce harmful gases. There's less damage to the landscape and they conserve supplies of high-grade ores, but they're super slow. Bioleaching doesn't require high temperatures, but toxic substances and sulfuric acid can be produced and damage the environment. Phytoextraction can extract metals from contaminated soils, but it's more expensive than mining some ores. Growing plants is dependent on weather conditions. So try to remember those. So give 2 advantages of extracting copper using bioleaching. Pause, see if you can do that, come back. Any 2, no harmful gases, less damage, conserves ores, doesn't need a high temperature. Any of those would give you those marks. Okay. Oxidation and reduction of metals. Corrosion is the reaction of a metal with oxygen, and this makes the metal gradually weaker over time. So if we found silver, gold, iron or copper at an ancient burial site, clearly the iron sword would have corroded, as rusting is a special case of corrosion of iron. It requires water and oxygen to be present. Aluminium is a reactive metal, yet we use it for storing our food because it doesn't corrode. This is because it can very quickly form an oxide layer over the surface called a tarnish, which protects the rest of the metal from corrosion. Native metals, very unreactive, found uncombined with other elements, we know this. Heating metal ores with carbon, displacement reaction, carbon displaces metals that are below it in the reactivity series, and electrolysis is the high energy, electrical energy way to separate metals from compounds. It's a more powerful method, but it's very expensive, and it releases the more reactive metals. So we've looked at oxidation and reduction in terms of electron gain or loss through oil rig. We can also define oxidation and reduction in terms of oxygen. Oxygen is the gain of oxygen by a substance, reduction is the loss. So in this particular reaction, carbon has been oxidized because it has gained oxygen, and iron oxide has been reduced because it has lost oxygen. So A to J, jot them on a piece of paper. And is the underlying substance in the equation oxidized or reduced? So you're just literally writing oxidized or reduced by each one. Pause. Come back when you're done. Well, aluminium oxide becomes aluminium, so it loses oxygen. Okay, so it's reduced. Nickel, however, gains oxygen to become nickel oxide, so it's oxidized. Zinc oxide loses oxygen, so it's reduced. Iron oxide loses oxygen, so it's reduced. Chromium oxide loses oxygen, so it's reduced. Copper gains oxygen, so it's oxidized. Copper oxide loses oxygen, so it's reduced. Calcium oxide loses oxygen, so it's reduced. Tungsten oxide, hydrogen gains oxygen to become water, so it's oxidized, okay, because hydrogen is H2 and water is H2O. And magnesium is oxidized to form magnesium oxide. Okay. Now, a little bit of the extra work for you. You will see that you are given the formulae of everything that you'd need the formulae for. Iron oxide reacts with carbon, you know that's C. To form iron, you know that's Fe, and carbon monoxide, CO. So they've given you Fe2O3 plus C goes to Fe plus CO, and you've got to just balance that. Okay, hopefully you got that one right. You can see that the iron oxide has lost its, the iron oxide has been reduced as it's lost its oxygen, and the carbon has been oxidized because it has gained oxygen. Okay, so pause and answer these ones. And hopefully you've come back. Again, you're given aluminium, you know, is Al, zinc oxide is given to you, aluminium oxide is given to you, and Zn, you know, is zinc. Hopefully you're able to balance that equation. Explain which substance has been reduced. Zinc oxide, as it has lost oxygen. And the one that has been oxidized is aluminium, as it has gained oxygen. Okay, now you've got to think in terms of oxidation and reduction. We have taken electrons away, copper's losing them, so it's oxidation as copper atoms lose electrons. Electrons have been adding here, so it's reduction as oxygen molecules gain electrons. Look, electrons being added, reduction. Look, electrons being separated, oxidation. Electrons being separated from the ion, so again that's oxidation. Okay folks, last bit of the video, recycling and life cycle assessments. The 3 R's, reuse things, reduce your use of things, or recycle and repurpose things. Why do we recycle materials? It saves energy, it saves raw materials, it saves environmental damage. There's loads and loads of very good reasons why we need to do that. In the UK, we use 13 billion bottles per year. Plastic is usually made from crude oil, which is non-renewable. It uses a lot of energy, and transporting uses fossil fuels, which is not biodegradable. Some can end up in the oceans, causing marine wildlife problems. Take up a lot of space in landfill as well. Just a little bit of data to look at, and some questions. So if you look at which metal is likely to run out first, well, we've only got 12 years of gold left, haven't we? Which method of extraction is used for aluminium? Well, we know that that's electrolysis, don't we? Because we've just talked about that. And we know that for iron, it's displacement, heating with carbon. And suggests why the way aluminium is extracted makes it more expensive metal than iron. Well, electrolysis, it uses more energy, doesn't it? More energy, higher cost. 2 advantages of recycling metals. Well, if you're going to recycle a metal, you're going to save raw materials, you'll save rocks and ores from having to be processed, you'll save energy, your costs will be less, there will be less damage to the environment through quarrying and all of that sort of thing. Okay. Disadvantage of recycling some metals, well, maybe the metal has been weakened by previous use and then it might not be suitable to be used again. So manufacturers, before they make anything, they do what's called a life cycle assessment, and it works out the environmental impact of each stage of a product's life. You extract and process raw materials, then you manufacture and package, then you use and reuse, and then you dispose, but you include in transport and distribution at each stage. So if you wanted to do a life cycle assessment for the yogurt pot, you'd have to think about what materials are used to make it, how do we get these materials, how will they be transported, can we reuse the packaging, how will the packaging be disposed of? All of those questions would have to be answered. It's interesting when you do a life cycle assessment because you don't always get the answer you might expect. So if we're going to have a look at which bag has a greater environmental impact over the course of its life, we would have to look at the life cycle assessment for paper bags and plastic bags in terms of raw materials. Are they renewable? Where are they found? How far do we need to transport them? Manufacture, what processes are needed for manufacturing? Distribution, environmental impacts of that, product use, how long does it last, does it have an environmental impact, can it be reused, and disposal of the product. Can it be recycled, is it biodegradable, blah blah blah. Okay, so when you want to do a life cycle assessment, you have to compare obtaining and processing raw materials, manufacturing and transport, disposing of the product and using the product for 2 corresponding materials to see which one's the best, in this case plastic and paper. So, plastic bags have a lower environmental impact. Even though plastic bags aren't biodegradable, they take less energy to make than paper bags. This is because so much energy is used to pulp the amount of timber needed. Even though crude oil extraction and processing uses a lot of energy, there is little waste, unlike paper production, and a lot of wood is needed to make paper bags strong. Finally, plastic bags have a longer lifespan as they can be reused. Lots to think about. Raw materials and processing. Paper, wood and chemicals for processing, large amounts of water, electricity from renewable sources, but produces ash. Plastic is fractional distillation of crude oil, followed by polymerization using electricity from coal-fired power stations. Manufacturing, paper uses electricity from renewable sources, but plastic bag uses electricity from coal-fired power stations. Paper bags produced in Europe, transported to the UK. They're in a lorry for 1,200 kilometres. Plastic bag produced in the Far East and transported to the UK. 600 kilometres in a lorry. 16,000 kilometres of sea freight and 280 kilometres on the railway. Okay, lots of environmental impact there. Paper bag, lightweight, tears easily, disintegrates when wet, but a plastic bag is lightweight and doesn't tear easily and is water resistant, so that's better. Paper bag needs to be reused at least 4 times to reduce its environmental impact to below that of a plastic bag. Plastic bags can be easily reused for shopping, bin liners and storage. Paper bags can be recycled or composted but release toxic metal compounds to the soil and water. Can be burned, but that would give you carbon dioxide and other chemicals into the air, and can only be recycled a maximum of 4 times before fibres disintegrate. Whereas a plastic bag can be reused but not recycled. Most are non-biodegradable, can be burnt but release carbon dioxide and other chemicals into the air. So exam questions would expect you to discuss the pros and cons of the various stages of the life cycle assessment, ladies and gentlemen. And I think that's all we have time for.